Hello, welcome to week one, Trinity Term 2021 of the Oxford Philosophy of Physics seminar. It is my incredibly great pleasure to welcome local hero, rising star, Caspar Jacobs. Caspar is a graduate of the MPhil program, then went straight into the BPhil and then straight from there onto the DPhil. He is currently just making the final finishing touches on his DPhil thesis, which is broadly speaking on the metaphysics of quantities and the role they play in explanations in classical theories, especially in light of gauge symmetries. And Caspar has been outlining a sort of a third way, if you like, between absolutism and relationism, otherwise known as comparativism. You might think, how could there be a middle way between a one-place and a two-place predicate? Well, it's complicated. But Caspar will be presenting on an aspect of his thesis here. But he's been very busy. He's also published on QFT and on the work of Emily de Châtelet, as well as being a convener of the Philosophy of Physics graduate lunch. And very happy to say he will be starting a postdoc at the University of Pittsburgh later this year. So congratulations, Caspar. And today he will be talking about comparativist theories or conspiracy theories, the no miracles argument against comparativism. Take it away, Caspar.
Great, thanks for the introduction, Adam. I should say, if anyone here was hoping to see some guy called Caspar Jacobs speak, then I'll have to disappoint you because it's just me. But hopefully this will be interesting, so I'll just dive straight in. So let me start by just explaining briefly this title, Comparativist Theories or Conspiracy Theories, the no miracles argument against comparativism. Basically, I'm advancing the thesis that comparativist theories are, in a sense, conspiracy theories, or in other words, that a particular type of comparativist theory that I'll introduce in more detail later is committed to postulating certain conspiracies or miracles or cosmic coincidences that we'll go and explain then. Obviously, I'll argue that this is a defect in such theory, so that it provides a reason against comparativism and in favor of absolutism. And that's sort of similar to this thing known as the no miracles argument. So recall that the no miracles argument says something like, if, for example, quantum mechanics were false, then it would be a miracle or a cosmic coincidence, or if you will, a conspiracy, that all the predictions of quantum mechanics turn out to be true, or at least highly accurate within its intended domain. And I'm going to claim that something similar is the case for many comparativist theories. Namely, if comparativist theories are true and they describe the world at the most fundamental level, then it's going to be a miracle or a conspiracy that certain structural facts about the observable world hold true. Whereas if absolutist theories are true, if they describe the world at the fundamental level, then those same structural facts can be explained or explained away, so they don't count as miracles. So that's the sort of very broad framework. And as Anna mentioned, this is connected to symmetries in physics, and I'll come back to that connection later. But I think today I'm sort of approaching this problem more from the metaphysical perspective. So we're interested in this debate between absolutism and comparativism, which, as I'll go on to explain now, is a question about what the fundamental quantities in nature are. So here is the rough plan for the talk. I'll start out by clarifying in a little bit more detail what this absolutism versus comparativism debate is about. Then I'll highlight one particular aspect of this debate having to do with fundamentality. Then I'll go on to the meat of the talk. So first, I'll give some examples of what I call comparativist conspiracies. And then I'll outline a proof which I've developed, which says that one particular class of comparativist theories will sort of always, or very often encounter such conspiracies. If we've got time, I'll go into some objections and responses, but I've put it between brackets because I'd like to spend some time on the proof outline. And the objection and responses we can deal with in Q&A if necessary. And then I'll conclude. Good, so as I said, this absolutism versus comparativism debate is a debate about what are the fundamental quantities of nature according to our best scientific theories. And I'm just going to start out listing some examples of this type of debate. So one very famous one is between positions in space or distances between bodies. So positions you can think of as absolute quantities. Distances are comparative in the sense that they compare, sort of it's a comparison between distances. Another one that's recently been discussed much is about mass properties. So the question here is, are the fundamental mass properties intrinsic, or are they instead relations between particles? So for example, mass ratios. And another one, this one occurring in gauge theories, one could think of locally defined fields, for example, the electromagnetic potential, as an absolute quantity. And I'll explain why that's an absolute quantity in a minute. And there's this alternative view, which says that instead the fundamental quantities for these classical field theories are so-called holonomies. And they, I will say, are comparative quantities. And again, in a minute, I'll say why that's the case. But this should give us a sort of feel for the type of debate that I'm interested in. And we can see that it's not contained to one theory. It applies to many different theories in contemporary physics. Good, so as I will understand absolutism, it's the claim that monadic quantities are fundamental. So monadic quantities, are properties of single entities. So for example, we've just seen these positions in space. A position is a property of a single massive or non-massive body. We can take one object and say, what is its location in space? And Newton obviously defended this position that particles have positions in space. In the case of masses, intrinsic masses are obviously monadic because they belong to one single particle. And absolutism of mass quantities has been defended by Armstrong and more recently by Niels Martens. And as I've said, local field values count as monadic quantities, and now we can see why, because they're properties of single spacetime points. So they're monadic because they're functions from spacetime points into some field value space. And this sort of view that the electromagnetic potential is the fundamental field was defended by Feynman. It's problematic because the electromagnetic potential is a gauge quantity, and we'll come to that later. Comparativism, by contrast, is the view that instead fundamental quantities are dyadic, so typically relations. And again, for example, in the case of spacetime, we've got distances between bodies, so Leibniz defended this view. In the case of mass, Des Gupta defended the view that the fundamental mass quantities, in Newtonian gravitation at least, are mass relations. Sometimes people will say they're mass ratios. I think that's a little bit fishy, because if you believe that the mass relations are fundamental, then they're not really ratios of anything, right? They couldn't be ratios of intrinsic masses. But for simplicity, I'll sometimes talk about mass ratios, being understood that it's sort of sketchy talk. And then field holonomies. So as I said, holonomies, and Healy defends this view, are properties not of individual spacetime points, but of loops of spacetime, loops in spacetime, and they've got a single holonomy value. So the sense in which these quantities are comparative is basically, one can think of it as if you've got two open paths in space, we can assign each open path a value which is sort of the integral or the exponential of the integral of the field. So that would be, as it were, a monadic quantity which is assigned to open paths in spacetime. And then the holonomies would count as properties of pairs of open paths that together form a closed loop. So in that sense, they're comparative. If that's too complicated, you can also think of it a different way. Instead of taking monadic and dyadic, take the distinction between monadic and polyadic. Then we can just say a holonomy is a property of a set of points, not two, but many, that together form a loop. And that will also yield the same sort of contrast. Good, so in a nutshell, the debate between absolutism and comparativism concerns the adicity of the fundamental quantities of nature. That's what I'm concerned about here. And obviously, I'm going to try and use physics to discover what the of the fundamental quantities of nature is. And now let me just briefly connect this to the question of symmetries. So one very natural motivation for comparativism is the thought that many absolute quantities vary under the symmetries of the theory in question. And this is actually true for all of the absolute quantities I mentioned before. So absolute position famously varies under translations in Newtonian spacetime. So that's a variant quantity. And people have often concluded that that means that we can't measure a body's position, right? And that's the case because, suppose I was trying to measure the position of a body, I would get some result in my measurement device. Now imagine that we've shifted the whole world 3 meters to the right, because that's the symmetry of Newtonian mechanics. My measurement device would yield the same result, but obviously I would be in a different position in space-time. So that sort of means that it didn't count as a genuine measurement of position. That's very rough argument, and there's much to say about that, but that's been a thought that's been persuasive to many people. In the case of mass, it's a little bit more controversial, and I'm not going to enter into that debate here, but at least some comparativists like Dasgupta have argued that uniform scalings of all masses are symmetries of Newtonian mechanics. So in that case, intrinsic mass would be a variant quantity. And in the case of the electromagnetic potential field, that one famously is variant under gauge symmetries. Good, so that's sort of the motivation to say these absolute quantities are suspect because they're non-measurable. And the goal then is to define invariant functions of those quantities, and those functions will often be comparative. So in the case of mass, for example, mass ratios are functions of intrinsic masses, but jointly they're invariant. So the mass ratios are invariant under uniform scalings. Similarly, distances are invariant under shifts. And then once we've done that, one could go a step further and define a new theory in terms of those invariant quantities. That's known as reduction. And yeah, so basically, this in the sort of broader picture, I'm thinking that the argument I'm presenting here works as an argument against these forms of reduction, because reductionist theories will be committed to the kind of conspiracies that I'm considering here. Good, so now I've said this debate is about what the fundamental quantities of nature are. What does it mean to say that some quantity is fundamental or that it is more fundamental than another quantity? So in the recent literature, fundamentality has been characterized in terms of what we can think of as a vertical relation between sort of different levels of quantities. For example, grounding. And I'm happy to accept that. I'm not going to argue against that, but I just want to emphasize a different aspect, which we can think of as horizontal. So it concerns the relation between fundamental quantities at the same level of fundamentality, if you will. And the sort of principle that I'm going to apply here has sort of been coined in different ways. So very broadly, we can think of it as modal freedom of the fundamental quantities, and I've got a few quotes that express this idea. So one way of saying it in a very general way is due to Do, and it says the only genuinely necessary truths are those that reduce upon analysis to truths of logic. So in particular, that means if we've got the fundamental quantities, anything that we can say that's necessarily true of those has to be a logical truth. That's very broad. Something slightly more specific is Hume's dictum. So here is an expression of Hume's dictum due to Wilson, who says there are no metaphysically necessary connections between wholly distinct intrinsically typed entities. Now again, that's a complicated statement, and there's a lot to unpack here, and I'm not going to go through that. A statement that's sort of more useful for my purposes is due to Jessica Wang, and it says that the fundamental properties and relations are modally free if and only if any pattern of instantiation of the fundamental properties or relations is possible. That's the notion of modal freedom I'm going to work with. And the thought here is that fundamentality entails modal freedom. That's the principle I will assume here. So if some property or relation is fundamental, then it is indeed going to be the case that any pattern of instantiation of those properties and relation is possible. So what does this mean in practice? For the absolute quantities, it means that any object within the theory's domain can instantiate any of the quantities values. And of course, it also means that they do so sort of separately or independently from each other. So if one body is 5 kilograms in mass, then that in no way constrains the mass of some other distinct object that could still have any of the values of the mass quantity. Now, I want to say something similar about relations, and I think that's in the contemporary debate a little bit more unusual. I think if you look at someone like David Lewis, who assumes a sort of a free recombination principle like this, on his worldview, you know, the mosaic, all we've got are intrinsic or monadic properties spread out over space-time. So all we need is sort of this statement. If we're considering the idea that some relations are fundamental, then I think it makes sense to say that we'll extend the assumption of modal freedom to those relations as well. So what that's going to mean is that any pair of objects within the domain can instantiate any of the quantities values, right? So if we've got two particles, then they could bear any mass ratio to each other. And if we've got another pair of particles, then their mass ratio is independent from the mass ratio of the first pair of particles. I think that's a necessary condition for what it means for mass ratios or mass relations to be fundamental. Good. And this is sort of similar to Adam Colton's idea of using Hume's dictum as a guide to what there is. So the idea here is if it turns out that some quantity doesn't seem to be modally free, then we can use this as evidence to say that those quantities are not actually fundamental, right? So if it turns out, for example, that there are systematic correlations between the mass ratios between pairs of bodies, then that should provide us good evidence to say that, in fact, mass ratios are not fundamental. And that's exactly the type of argument I'm going to use here. Good. So now let me give some examples of exactly those type of conspiracies. So these are examples of cases in which a quantity, a comparative quantity that's set to be fundamental doesn't seem to be modally free. It doesn't seem to freely recombine in a way that Hume's dictum dictates. So none of these examples are mine, but I think I'm sort of, you know, I'm trying to pull them together and show that actually they all point to one phenomenon. And then in the proof outline, I'll sort of unify these examples and show why they occur. So the first example, due to Maudlin, is the triangle inequality. So the idea is in a Newtonian world, in fact, not only in a Newtonian world, but just for simplicity, let's suppose a Euclidean space, then we know that the following relationship between distances must hold. So suppose that A, B, and C are three particles that we've got, then we know that the distance between A and B added to the distance between B and C has to be equal or greater than the distance between A and C. So that's known as a triangle inequality. Now, if distances are defined as displacement vectors between points in Euclidean space, then this constraint reduces to a mathematical theorem. So in that case, you know, we've got these three vectors in Euclidean space, and we should be able to prove in a few lines of mathematics that these vectors are always going to satisfy this inequality. I should say I'm being a little bit careless here in sort of confusing physical and mathematical language. So distances as a physical quantity obviously are not identical to displacement vectors, which are sort of mathematical objects we use to represent distances. So if we were going to be a little bit more careful here, we would say something like, if it is the case that distances are such that we can always represent them as displacement vectors between points in Euclidean space, then this constraint reduces to a mathematical theorem at the representational level. But in the rest of the talk, I'm sort of going to confuse those two levels of representation and physical a little bit, and it should be understood that that's maybe not quite legitimate, but I hope it's not going to cause any problems. Good. So if you know, to say the same thing in a more metaphysical language, if we think that distances supervene on positions, then we can explain why the triangle inequality holds. It's a consequence of the fact that space-time has a Euclidean structure and that particles are located within Euclidean spacetime. So we don't need to say anything further. We don't need to say anything about distances in addition to the fact that there are displacements between points in our spacetime. But if distances are fundamental, then by the principle that fundamentality entails modal freedom, it seems that the triangle inequality could easily have failed, right? Because that means we sort of have to block out the second equation on the slide and only look at the first equation. Now, by the fact that distance is a fundamental quantity, we want to say that each of these three values here, so the distance between A and B, the distance between B and C, and the distance between A and C, could have had any value whatsoever. So yeah, so they could have had any value whatsoever, and in particular, they wouldn't need to satisfy this constraint. So that's why it seems that it's a cosmic conspiracy if we're being relationists like Leibniz was, right? It seems that there is no explanation for the fact that distances satisfy the triangle inequality. There is no deeper fact about the structure of space that we can appeal to, because if we believe that distances are fundamental, we don't believe that location in space is a fundamental quantity. Good. So I should say, by the way, just as to avoid any confusion, I've also been a bit careless here in the distinction between distances and displacement vectors. So really, distances obviously we can think of as the absolute value of the displacement vector, not taking into account the direction. So yeah, just wanted to note that before anyone got confused. Good. So second example follows a very similar structure. This one's due to Martens and Reed. So in a Newtonian world, the following relation is satisfied. Here, MIK is the ratio between the mass of somebody I and the mass of somebody K. And that ratio is equal to the product of the ratio between the mass of I and the mass of some third body J times the ratio between the mass of J and K, right? So this is very easy to see if we suppose that I, K, and J all have the same mass, right? So if I've got a 1 kilogram stone and a 1 kilogram piece of fruit, then their mass ratio together is 1, right? They've got the same mass. Now suppose I've also got a 1 kilogram bag of sugar, then the bag of sugar and the 1 kilogram piece of fruit also have the same mass. And it follows from that that the bag of stone or that the 1 kilogram stone and the bag of sugar have the same mass, right? So the fact that I and J have the same mass and the fact that J and K have the same mass entails that I and K have the same mass. Now, again, if mass relations are defined as ratios between intrinsic masses, taking care of the same caveat that really mass relations can't be ratios because they're physical properties, not mathematical properties. But that aside, once we identify mass relations with ratios between mass properties, this constraint reduces to a mathematical theorem, because we can just write out MIK as the literal ratio between MI, which will denote the intrinsic mass of our particle I, and MK, which will denote the intrinsic mass of our particle K. And we can see that in one line, this is just going to be mathematically true, right? But the comparativists about masses can't appeal to this explanation of this relation, which we can call the transitivity of mass ratios. And the reason they can't do that is because in this explanation, we're appealing to things like MI and MK, which are supposed to denote intrinsic mass properties. But of course, the comparativist believes that intrinsic mass properties are at least not fundamental, and usually they argue that intrinsic mass properties don't even exist. So that means that it's illegitimate to make use of such properties in an explanation of a relation that holds between fundamental mass relations. Right? So instead, as before, by the claim that fundamentality entails modal freedom, it would seem that this relation could easily have failed, because it would seem that MIK could have had any value, MIJ could have had any value, and MJK also could have had any value. And because those are all fundamental quantities, it should be the case that the value of one of those or two of those doesn't constrain the value of the third one. So again, for the comparativist, it's a cosmic conspiracy that this relation, in fact, does seem to hold, right? Whenever we have three bodies, three particles, it seems that this is always true, right? And of course, it needs to be true because Newtonian mechanics as we use it is a theory which posits intrinsic mass properties. So for the empirical adequacy of Newtonian mechanics, it would indeed need to be the case that this thing is true, right? So to refer back to the no miracles argument here, the problem for comparativism is that if comparativism is true, it is a miracle that Newtonian mechanics formulates in terms of intrinsic masses is empirically adequate. Because if we posit intrinsic masses, then this relation is always going to be satisfied. But for the comparativist, there is no reason to believe that this relation will always be satisfied because mass relations are fundamental. And the third example follows a very similar chain of reasoning. So Arnzenius talks about this. Basically, there are certain relations between holonomies that we get when we take the concatenation of loops in space. So here, L1 circle L2 is sort of the result of taking L1 first, you know, say one circle, and then taking L2 going around the other circle. That will itself also be a closed path in spacetime. So we can assign it a holonomy. And it turns out that that holonomy is always going to be identical to the product of the holonomies of the individual parts L1 and L2. Again, if we, I'm sorry, I should have said holonomies here instead of mass relations. So ignore this. If we define holonomies as the integral of the electromagnetic potential field A over you know, this particular loop, so like this, then it's just going to roll out that the product of the holonomy around L1 and around L2 is going to be the same as the holonomy around L1 concatenated with L2. But again, it seems that someone who thinks that loop holonomies are fundamental, that they don't in fact supervene on the distribution of the A field, can't avail themselves to this explanation of this relation between loop holonomies, because the explanation appeals to the electromagnetic potential field A, which, according to someone like Richard Healy, doesn't represent anything physical, so you shouldn't be able to figure in a physical explanation. So, but if holonomies are fundamental, then again, by fundamentality entails modal freedom, it would seem that this relation could easily have failed, because the holonomy value of one closed loop in spacetime and the holonomy value of another closed loop in spacetime, they should have nothing to do with each other. They're independent from each other. That's what it means, on my understanding, for those quantities to be fundamental. Good. So there are some further examples. So Jura, for example, mentions the fact that handedness is an equivalence class. Roberts and Jura both mentioned the idea of forces being conservative. That sort of follows from the fact that forces are gradients of potentials. Niels Martens mentions the conspiracy of inertia. I put a question mark there because I'm less sure if it fits the mold. In particular, it's unclear in that case what the absolute and what the comparative quantity is. So I'm not exactly sure that this is an instance of the same thing, but I put it here because Niels Martens thinks it is. You know, I think the sort of the multiplication of these examples should convince us that this is in fact a widespread phenomena, and that maybe conspiracies of this form are in fact pernicious to comparativism. And to test that hypothesis, I've sort of outlined a proof which shows that indeed, under certain assumptions, comparative theories will invariably encounter comparativist conspiracies. So I'm just going to outline the proof. First, we're going to posit certain objects. So we're saying let D denote the theory's domain. So for example, that could be a domain of particles. We're going to let curly A denote the value space of the absolute quantity. So by a value space, I sort of mean a mathematical space which represents the values of said quantity. So if we're thinking of mass, for example, then mass value space is a structure, a mathematical structure, such that each element represents a mass property, such as the property of being 5 kilograms. Very often people take this to be just a structure of something like the positive real numbers, such that mass is a function from the domain of particles into the real numbers. I think that's not quite right. I think that the real numbers have, in a sense, too much structure to represent a quantity like mass. because, well, basically it seems to endow mass with a privileged system of units, but I'm not really going to go into that. So for now, I'm sort of happy if we assume that it's just going to be the positive real numbers. But in general, this is going to be some sort of structure, for example, a semi-group. And same thing for the relational quantity. So that too, we've got a value space, which is usually distinct from the first one. It could have a different structure. And the elements of that value space represent the values of the relational quantity. So for example, mass relations. So then we've got the absolute quantity M, which is a function from the domain into the absolute value space. So for example, a function from particles into mass value space. Likewise, we've got the relational function, which, because it's dyadic, is going to be a function from pairs of the elements of the domain into the relational value space. So, for example, a function from pairs of particles into the value space of mass relations. And finally, we're going to have a group of symmetry transformations, G, and this connecting it back to the literature on symmetry. So I'm now considering a particular form of comparativism, which is interested in coming up with a reduced theory which deals solely in terms of quantities which are invariant under this particular group of symmetries, G. Good, so those are the objects we're assuming. Now we've got some assumptions. So the first thing we're assuming is that Rij, this function from pairs of, say, particles into the space of mass relations, can be expressed as a function, I've called it R bar, from values of the absolute value space into the relational value space. So what does it mean? It basically means that we can, as it were, translate between the relational quantity and the absolute quantity, right? So in the case of mass, we can say, well, let's start with the assumption that we've got intrinsic masses. Then given two particles and their intrinsic mass, we can then deduce their mass ratio, and that will give us the value of the relational quantity given those two particles. So the reason we need this assumption is basically for the reduced theory, which deals solely in terms of the comparative quantities, to recover the empirical content of the theory which we started out with, which posits absolute quantities, right? So the theory we started out with does say that there are absolute masses, and we better be able to say, given a model of the theory of absolute masses, which mass relations it assigns to each pair of particles, because then we can map it onto a model of the reduced theory, which talks only about mass relations. So that's one crucial assumption. Then the second assumption is that this group of symmetries G has a free intransitive action on the space of absolute values A, right? So if we think of mass values here, for example, the group of symmetries G, and as I've said, it's sort of controversial whether this is a symmetry, but suppose it is, then the group of symmetries will be the group of uniform scalings of all mass values. So that would have a free intransitive action on A, meaning that for every pair of elements of A, so for every two mass values, there is a unique element of that group, so a unique mass scaling, which takes the first mass value into the second. So to give another example, consider A to be a Euclidean affine space, then G will be, for example, the group of translations. And the group of translations is such that for any pair of points in Euclidean space, there is a unique element of G, a unique translation, which takes you from one point to the other. So this is quite a strong assumption. So for example, rotations are not free and transitive, because they've, as it were, got a fixed point. So if we've got the point around which we rotate, then it's not the case that only the identity transformation takes that point to itself. Any rotation around that point takes that point onto itself. So, that's one of the limits of the theorem. And then the final assumption is an invariance assumption. So we're saying that for any pair of values of the absolute value space, and for any other pair of values of the absolute value space, they map onto the same relational value if and only if they're both related by the same symmetry transformation. So again, take Euclidean space as an example. Given any pair of points in Euclidean space, And given any other pair of points in Euclidean space, the displacement vector between those 2 points is the same if and only if those points are related to each other by the same element of the group of translations. Or similarly, if we're talking about the mass quantities, take a pair of mass quantities, their ratio is the same as the ratio of another pair of mass quantities if and only if both pairs of mass quantities are related to each other by the same scaling transformation, right? So if I've got the pair 1 and 2, their mass ratio is 1/2, and I've got 2 and 4, their mass ratio is also 1/2. And indeed, we go from 1 to 2 by doubling 1, we get 2. And similarly, if we double 2, we get 4. So indeed, there it is the case that both pairs of quantities are related to each other by the same transformation. Good, so those are the assumptions. Now we've got the results, as it were. So I'm not going to give all the details, but a few important results. So the first is we can establish a bijection between the absolute value space A and the group of symmetry transformations G, and one that, as it were, respects the relational structure of this value space. So this immediately follows from the fact that G has a free and transitive action on A, because what we can do is we can simply take any arbitrary point in A, call it X. Because G is free and transitive, it follows that every other point in A has a unique element of G, such that that element of G takes X to the other point, and we can simply identify that point with that transformation of G, right? So for example, take any arbitrary point of Euclidean space. For any other point in Euclidean space, there is a unique translation from the first point, which takes us to the second. So we simply identify that second point with that translation. Good. A little bit more interesting is that we can also establish a bijection between the relational value space and the group of symmetry transformations. And that bijection is sort of set such that, but this is just sort of giving that bijection. So the claim is this thing I've defined here is a bijection between R and G. So what does that mean? That means that for every relational value of the relational quantity, we can identify that value with an element of the symmetry group. And again, we can see how that works, for example, in the case of Euclidean space, because any pair of points in Euclidean space is associated with a relational value. And we can sort of think of that relational value as the displacement vector. But of course, displacement vectors also generate the group of translations. So each displacement vector, in fact, gives us a translation. So what we do here is we're simply saying, well, let's identify the displacement vectors in Euclidean space with the group of translations in Euclidean space. And from that, and this is sort of the interesting thing, we can define an inverse function to R. So this one takes an element of the absolute value space and an element of the relational value space and gives us a new element of the absolute value space. So for example, again, in the case of space-time, it takes a point in Euclidean space, a vector of our vector space, and that gives us another point in Euclidean space, namely the unique point, such that X and Y together, the displacement between them is exactly the displacement vector V. So yeah, this is sort of the thing we're interested in, this inverse function of R, because what we can prove about the inverse of R, if R is invariant under a regular group action of G on A, as we've assumed, then this inverse function of R represents a regular group action of R on A, meaning that A is a principal homogeneous space for R. So that's a lot of terminology. So let me just explain what that means. Basically, the best way to think of it is think of R having, at the very least, a group structure. So at the very least, we can take two elements of R and take their group product, giving us another element of R, such that there exists an identity element. So there is an element of R such that the product of that element of R with any other element gives back the other element itself. Every element has an inverse, and the group product is associative. So when that's satisfied, we can say that R is a group structure. And now a principal homogeneous space is, as it were, a group that's forgotten its origin. So for any group, we've got a unique identity element. A principal homogeneous space is like a group, but without an identity element. So that's maybe a bit vague, but again, Euclidean space is an excellent example. So first think of a vector space. A vector space has an identity element, the zero vector. We can think of an affine space as a vector space without an origin. So it's homogeneous, it's the same everywhere, just like Euclidean spaces. But of course, we've still got a sort of a secondary structure, namely that each pair of points in Euclidean space is associated with a unique vector of the initial vector space. So we're still, as it were, retaining a sort of a distance or a comparative relation between points of our principal homogeneous space. So that's sort of an interesting type of structure that's not been studied very much by philosophers, but quite recently, Neil Jura has done some work on this. So principal homogeneous spaces apparently have multiple applications in philosophy of physics, and this is one of them. And I'll just briefly sketch the proof of this theorem, but the proof isn't super interesting. But basically, we can say, as we know, we've got a bijection between elements of the values, the relational value space, call them V, and elements of the group of symmetries G. So we can simply label every element of the relational space VG, right? That's going to be the element of the relational value space associated to the transformation G. And then we can define a group multiplication like this, because we know that R, as it were, inherits the group structure of G. We know that this, in fact, gives us a group. So that's what I've said here. And now we only need to look at the action of this group via this operation plus on the absolute value space. So we're saying take any point in the absolute value space. If we act on that point with the vector Vg, then we get back whatever we would get when we act with G, an element of the symmetry group, on that point X. Right? And recall that we started out with an assumption that G had an action on A. So this thing here is well defined. Good. So when we do that, we can prove that plus satisfies the conditions for being a regular group action. So there's an identity, it's associative, and it's regular, meaning that for any pair of elements in A, there exists a unique vector between them. That's actually something that we already showed in lemma 3. So I've just repeated that here for convenience. And these three things together imply, by definition, that A is a principal homogeneous space for R. Good, so that's sort of all the mathematical work, and then the interesting thing is really a corollary to all of this, namely that once we've done all this, we can prove that for any triple of elements of the domain, so say for any triple of particles, the relational value between I and J, product with the relational value between J and K, product the relational value between K and I, has to equate to the identity. Here I being the identity of the relational value space. So it's really sort of V identity, the element of the relational value space associated with the identity element of our group of transformations. Good, so what does this tell us? Well, we know that because R is a group, this thing has a unique inverse. So we know that if we take, for example, just the product of RJK with the, or just the relation between J and K, product with the relation between K and I, we know that that has to be identical to the inverse of this thing, Rij. So that means that once we know these two things, once we know the relation between J and K and the relation between K and I, we've uniquely fixed the relation between I and J, right? And to relay that all the way back to the point we started out with, that means that we've got a cosmic conspiracy here. That means that we've got a failure of the principle of modal freedom or free recombination, because it tells us that once we know the values of the relation between I and J and the relation between J and K, there is no longer any element of freedom for the relation between I and K for this quantity, right? So for example, once we know the distance between, or the displacement vector between 2 points X and Y, and the displacement vector between 2 points Y and Z, it automatically follows uniquely determines the displacement vector between the points x and z, right? And that's going to be the case for any relational quantity which is invariant under the group of symmetries and which is expressible in terms of the absolute quantity we started out with, right? Those were the assumptions we started out with in this proof. So, in practice, that is going to be the case for all the examples we discussed. So, I've sort of used the space-time example as a running example. It's also going to be the case for mass quantities. And in fact, it's also going to be the case for holonomies. That one takes a little bit more work, but we can show something very similar. And in a way, in the sort of holonomy structure, if we express it in terms of fiber bundles, we've got a very obvious group structure there. So it's in fact a little easier to show that there is this bijection between the value space and G, because in a sense, the value space of the principal bundle is G. But that aside, so that's sort of the main result. How much time do I have, Adam?
You started just a couple of minutes late, so I'd say you've got 15 minutes.
Good. Well, let me do some of the objections and responses then, but I'll go through it reasonably briefly so we can discuss it in the Q&A as well. So here is a pair of objections against what I've said, and they sort of go together. So the first step is to say, well, the absolutist is also committed to conspiracies of the same form as the comparativist. And the reasoning here is, take, for example, the triangle inequality. As I've stressed, the fact that the triangle inequality holds is a consequence of the fact that bodies are located in a Euclidean space. But of course, space didn't have to be Euclidean, right? It could have been non-Euclidean, in which case the triangle inequality could have failed. For example, in Minkowski spacetime, we instead had the reverse triangle inequality. So, the absolutist also has to posit something. They have to posit that spacetime has a particular structure, which makes sure that something like the triangle inequality is satisfied. But then we can sort of ask, well, is that any better than just directly positing that the triangle inequality holds for fundamental distances? So that's the second prong of this response. The comparativists, instead of calling these relations conspiracies, they can just say they're laws of nature, right? It's just a law of nature about distances. That distances satisfy the triangle inequality. What's wrong with that? So to put it differently, even for the absolutist about space, a failure of the triangle inequality is metaphysically possible, namely, if space has a different structure than it has according to our theory, for example, Newtonian mechanics. Of course, it's physically impossible for the triangle inequality to fail for the absolutist because it's part of the laws of classical mechanics that space is Euclidean. But the comparativists can take the same line, right? They can also say it's physically impossible for the triangle inequality to fail if we just posit as a fundamental law that distances satisfy the triangle inequality. So it seems that the theories are on a par. In both cases, it's the case that the triangle inequality is physically impossible to fail, but metaphysically it could fail. Good, so I've got some responses to these objections. So the first one is sort of focusing on the absolutist explanation and saying actually there is a sense in which the absolutist explanation of the triangle inequality in terms of the structure of space as being Euclidean is more satisfactory and in particular more unificatory than the explanation of the comparativist, which simply posits the triangle inequality as a new law of nature, right? And I think, at least for me, that has some intuitive appeal. It seems that, once we posit Euclidean space, the triangle inequality rolls out, whereas the comparativist has to posit it separately as an additional postulate. So that's sort of the intuition. And I think we can make that intuition a bit more precise by thinking of, in this case, the structure of space, but we can similarly think of the structure of some value space as being the common cause of the fact that something like the triangle inequality or one of the other conspiracies holds at every time and every place, right? So think about the conspiracies about mass values, for example. If you're an absolutist, you only have to postulate once the structure of mass value space. And we're assuming that that's some sort of space of universals with second order relations between all the determinate mass values. that's just going to exist throughout space and time. And then it follows from the fact that every particle, wherever and whenever it is, has some value in that universal value space. It follows that it doesn't matter. Any three particles will satisfy the transitivity of mass ratios. But if you're a comparativist, in a sense, you're just baking that in. You're saying, you're quantifying overall particles at all times, and you're saying for any triple of particles, wherever and whenever, they satisfy the triangle inequality. So there is nothing that unifies the fact that the triangle inequality, or sorry, in this case, the transitivity of mass ratios, holds throughout space and time. So that's the sense in which it's less of a unification. It's sort of, so far we've observed that all triples of particles, their masses are transitive, their mass ratios are transitive, but why is it the case that that's also going to be true for any particle I'm going to study in the future? Well, for the comparativist, that's just the way the world is, as it were. For the absolutist, that's because all particles take values in the same mass value space. Good, so that's one side of my response. The other side is to say that actually the comparativist explanation is also bad because it violates the principle of locality. So again, this is not very precise, but I'm just going to give a flavor of the intuition. The idea is, for the transitivity of mass ratios to hold with physical necessity, it has to be the case that if the mass relation between I and J were different, then either the mass relation between I and K would be different, or the mass relation between J and K would be different. Right? If that's not the case, then the transitivity of mass relations fails. And if the transitivity of mass relations fails, then it seems that in fact it's not physically necessary. Right? If it's the case that if two arbitrary objects, these objects here, had a different mass relation, if in that world mass relations would no longer be transitive, that seems a weak basis on which to say that the transitivity of mass relations is a law of nature, right? So we're saying that if that were the case, then one of these two mass relations would also have to be different. But what that means is that relational facts about K, right, either the mass relation between I and K or the mass relation between J and K, have to counterfactually depend on relational facts about I and J, right, the original two objects, even though K could be, some arbitrary body located very far away from I and J. So it seems that there are some facts about K which causally depends on facts about I and J, even though these things are located very far away. I think that seems to violate some sort of principle of locality. We can also see why the absolutist isn't committed to the same failure of locality. Of course, for them, it's also true that if the mass relation between I and J were different, then one of the other two mass relations would have to be different. But for them, that's simply a consequence of the fact that mass relations supervene on intrinsic masses. Right? So obviously, it's the case that if my cup of water becomes more massive, then the mass ratio of my cup of water to this object also changes. But that's just because that relation supervenes. It's what is called an internal relation. So it supervenes on the intrinsic properties of both objects. And I think that doesn't violate the same principle of locality, because we can say, well, the relation isn't fundamental, right? And when we think for the fundamental quantities, it can be the case that these sort of depend upon each other in this way because of this supervenience relation. I think that's something very familiar. That sort of happens all the time. If I take a step to the left, then my distance with respect to everyone else in this Zoom meeting changes. Seems like spooky action at a distance, when in fact that's just a consequence of the fact that my distance to everyone else depends on my location and on everyone else's location. So if my location changes, then all those distances change as well. Good. So that's sort of in brief my response to these objections. So now for the conclusion. So I think if everything I've been saying is correct, then it seems that comparativism and reduction, and in particular this combination, so comparativist forms of reduction, forms of comparativism which posit relational quantities, which in addition are invariant under the theory symmetries, that combination of views seems to be in trouble. That also seems to imply that, contrary to orthodoxy in philosophy of physics, the absolute quantities, which are symmetry variant, are perhaps physically real, right? Because they figure in the explanations of those cosmic coincidences. So my argument should give us some reason to believe that objects really have definite locations in space or in space-time, that particles really do have intrinsic masses, and that points of space-time really do have field values locally defined at those points in space-time. But that sort of would mean that many of those variant quantities are more than just mathematical artifacts. They seem to represent real physical structure. And now, of course, the whole reason why we want to get away from these variant quantities is because they imply this undetectability, and relatedly, they imply a form of underdetermination. So the symmetry-related worlds seem to be empirically equivalent, and there's no experiment that we could do to determine if we're located here or located 3 meters to the right, as it were. So that leaves us with a puzzle, because now it seems that absolutism has an advantage, but also a disadvantage, and likewise for comparativism. So in order for this to really clinch the deal for absolutism, we have to solve this issue of underdetermination. Now, that's something that I haven't done in this talk, but that I have been working on, as Adam said in the introduction, and that's this view known as sophistication-led symmetries, originally coined, I think, by Neil Dewar. So the idea is sophisticated substantivalism is a well-known example of this. We can in fact say that worlds relate, or models related by a translation or a static shift, are in fact representations of the same possibility rather than representations of distinct possibilities. And that would help us avoid any issue of underdetermination. So I've been trying to argue in my default thesis that the same is going to be true for non-spatial temporal quantities like mass, or like those gauge quantities. So that too, we can say that symmetry-related models in fact represent the same possibility rather than distinct possibilities, and this avoids underdetermination. And I think that combination, so the combination of, on the one hand, postulating these absolute monadic quantities in order to explain cosmic coincidences, but on the other hand, also appealing to this view called sophistication to avoid underdetermination. That seems to me this really powerful third way that is really a best of both worlds view, to extend the analogy with the no miracles argument. So good, I'm going to leave it there. Thanks everyone for listening.